Thanks. I'll begin with a word of prayer. Dear Father, we thank you for this day. Thank you again, Lord, for these students. Just pray you help us today to just wrap up our thoughts for the final, Lord. In your name I pray. Amen. There's one sort of piece of low-hanging fruit that I should mention to you guys before I forget. It's, I mean, there's a lot of probably pretty simple theorems that we could have proved along the way that we haven't. Here's one. If you have a subring of an integral domain, what can you say about it? Yeah, I believe it's not hard to show that it says that S is an integral domain, provided what? There is something we need there. It's not empty. I think we need that one is in S. I mean, right. And I think we also need that one is. I mean, there may be. I don't know. Let me put some question here. I haven't actually proved this, but there's got to be some conditions that you can add here to make this true. Yeah, it seems like a good final exam question. So, more to my point, consider the Gaussian integers, right? And suppose you have an ideal. All right. And I guess for this to make sense, I feel like this ideal needs to what? I mean, I feel like we're going to have trouble claiming that Z mod I is an integral domain. Is that an integral domain? What's that? If what? If I is prime. Ah, very good. So this is an integral domain. If and only if I is prime. Okay, very good. So in fact, we already have the condition we need from our previous discussion, don't we? How do you decide if I is prime or not? I mean, I guess you can go from the definition, right? What's that?
I guess, kind of gets around the point where you could just prove that field is an integral domain.
Wait a minute, what field?
Or that.
Who said anything about a field? That's actually my point. Go on.
You could just prove that ring is an integral domain.
Oh, okay. I see. So you think it's easier just to ask the question, are there any zero divisors in the quotient? Okay, I think I can believe that. Well, suppose it is prime, all right? And set aside some of the subtle questions that probably are invoked by my implication up there. What can you say about this integral domain? I mean, geometrically, what's the deal? How many things are in this integral domain? We've looked at this for a few different cases, right? It's always the case that there's some sort of like fundamental region that gets repeated over and over and over again, right? So, is the Gaussian integers a principal ideal domain? In other words, is every ideal principal? Yeah, right? Because it's a Euclidean domain, which implies it's a principal ideal domain, right? So, yeah, every ideal is principal, which means I is generated by some basic generator, right? So I is equal to something, right? And then we have that theorem that the only other generators for this principal ideal are its associates, right? What are the associates in the Gaussian integers? Right, so just what you said. This, or this, or this, right? I mean, so long story short, basically there's, you know, here's the origin, there's one point, there's another point, there's another. I mean, it's there's some kind of like fundamental cell. I don't know exactly what it looks like, but it's something like that. These four. Anyway, you can go, you know, in sort of four fundamental directions on the from the origin, and those will give you this grid of points which we identify with I, right? How many representatives are there going to be? I mean, I don't know. The details are complicated for a given ideal, right? We've seen ones with 5. I almost assigned you one on the test that had 2, but I thought it would be too confusing. Do you know how you guys can get just 2? How about this? 1 plus I. If you look at the ideal generated by 1 plus I, so you get here, this goes to there, minus 1 is over here, right? And I think, I'm trying to remember, I think it's basically you either get this or the middle thing is the other one. So there's the ideal and the things that aren't in the ideal. There's just 2 things. Yep.
Wasn't there something about like finiteness of that, or am I mistaken? But didn't we have a theorem early on? Talked about some sort of integral domain stipulation, as long as it was finite.
Well, that's what I'm trying to get at here, albeit slowly. This is going to be finite, right? I mean, yes, there's an infinity of points, but we're identifying infinite sets of them in a regular way. At the end of the day, you have a finite number of representatives. We've seen this. So we have an integral domain, which is a finite integral domain. What did we prove about that? It's been a few days since we proved it, but we proved any finite integral domain is a field. So it should be completely unsurprising to us on the last test that when we looked at the quotient, we ended up with a field, right? That field happened to be Z5. But anyway, I'm just pointing out there's some, you can kind of use the things we've learned to gain deeper insight into a given example if you're just courageous enough to do it. So anyway, I will shut up. That's all I have for you today. So your questions? Yep.
Imagine yourself as a student of talking.
Imagine myself as my student. Okay, yes, go on.
You're trying to figure out out of the vast and depth and broad amount of knowledge that has been covered this semester, what sorts of things should be focused on and highlighted? What direction you should go?
I would look at the things we covered.
Oh, out of those.
There's a subset that would be.
I would say you should look at the. I should say, well, certainly the things. Sure, the things which were interesting, I think, is the ones you should focus on.
Is that interesting to you or interesting to us?
So maybe we only have to answer.
I found most of this first lecture interesting.
This is boring.
Yep.
Simple. I demand a new problem.
Homework notes. Where would you suggest starting when we study?
Well, I
What
would.
do you want us to emphasize in terms of test homework notes?
Well, I want you to understand what we've won over this semester, right?
He's not noticeable.
Here to
I mean,
assign percentages of
personally,
covered on final.
is Miss Chu here? I'm not seeing her. Right? Okay. I mean, personally, I always start with tests. Not because I'm going to ask those same test questions again, but because those tests, what I got wrong on a test, reveals to me most clearly what it is I didn't know.
Will you be
And,
focusing more strongly on like second and third tests and not first? Or?
Oh, I don't know. It's comprehensive. I will tell you this. I plan to have office hours Monday, probably, can you, oh, back to Tori. I hope to have office hours Monday, and couple hours in the middle there. I'll send you an announcement about that when I have it. I mean, obviously you need to know definitions of the central things. I mean, if you think back about, I mean, definitions are lifeblood, right? If I ask you something about, next to you, you know, the cyclic, what about cyclic groups, and you know, if you don't have a clear in your mind what's the definition of a cyclic group, it's really hard to answer that question, isn't it? So I think definitions are, you know, key. That's kind of like a no-brainer. Then I would say major theorems are important, right? Like, what's the major theorem about cyclic groups? We had a very clever name for it. It was the fundamental theorem of cyclic groups. What did that theorem say? Very good. Don't remember.
I know the definition of this.
Them's fighting words. Let's see here.
That if you have an element of order something, then the cardinality of the group generated by that element is cardinality of the group divided by the order of that
Here, let's take the mystery out of it. I mean, basically the fundamental theorem of cyclic groups says that if you have a cyclic group of order n, and k is a factor of n, then not only is there a subgroup of order k, there is just one subgroup of order k. So if I have a cyclic group of order 10, well, there's going to be a subgroup of order 2. There's going to be a subgroup of order 5. There's not going to be two subgroups of order 2. There's not going to be two subgroups of order 5. There could be multiple generators for said subgroups, right? And that's an interesting question. How many?
number of generators given by the speed function.
Indeedly. You are correct, sir. Yes, the Euler phi function loomed large in our thinking. That is true.
You're talking like with the problem in test 2 where it was like 1 similar to generator 5, I think it was. Yeah.
Sorry, let me continue handing these back while I don't answer your questions. Leah? How dare she? Let's see here.
The first time.
What's that? Her brother is more important than abstract algebra. Oh. Mr. P, back behind you. Can't put your family before abstract algebra? How dare she? See here. But sometimes I come to the help session and it's just me, so I don't see the relevance.
We're just waiting for the video.
I have to work.
Yeah. No, it's fine. So here it is in all of its glory. First of all, every subgroup of a cyclic group is cyclic. If you have a divisor of the order of the group, not only is there a subgroup, I mean, any subgroup has to divide the order of the group, the order of the subgroup rather. And there's a unique subgroup of each order, which divides the order of the group. So this was very useful for what? It's actually kind of more useful when it's not a cyclic group, right? Because if you find two subgroups of order 2, game over. Not a cyclic group, right? So a lot of the questions we asked were of that form. Questions? So, I mean, if you think back, what did we know about isomorphism on test 1?
How to do it.
I don't think we knew what isomorphism was on test 1, did we?
Yeah, I don't think we did.
That is that's a trap. That was a trap. We had yet to introduce isomorphism at test 1. I know it seems like forever ago, but
That was like the first 100.
on test 1, all we knew were cyclic groups.
Abelian.
And we should have become the master of how to calculate in a dihedral group at that point, right? So, is Carl here? Is his brother in town? What's going on here? All right. Yes.
Oh, yeah.
Quiet! It is kind of ironic that you have to shout to make people quiet. Anyway, go on.
Is it like, for the dihedral groups, when you calculate it, is x to the n y equals y x to the negative n?
Yeah, I think after the dust settled, we learned that the fundamental relations for the dihedral group were, of course, that, I mean, we proved, of course, you should be able to reproduce the proof of this, but usually we present the definition like this, right? And x to the n equals to 1. And I guess I can put that in there. I don't know if I even need that. I'm not sure. Let's just put it. It's true anyway. I mean, this is essentially, you could take this as the definition in terms of, things of the form x to the n, y to the n, form the dihedral group. Well, n is a bad choice. J. Things like this are in the dihedral group subject to these conditions. And what do you say? We basically proved that, how's it go? X to the j, y is equal to y times what? X to the what? Negative j? I think we agree. But the interesting thing, of course, just looking back on things, was we saw that what was the sort of interesting observation we made about all of these elements? Yeah, these all have order 2. Now that's it kind of depends on the question, right? If my question on the final is show that all of the elements in the dihedral group, about half of the elements in the dihedral group, depending whether n is odd or even, have order 2, and you tell me, well, those have order 2 in the dihedral group, I will be unimpressed, because the whole question was to show me why that's true, right? Using those algebraic conditions. On the flip side, if there's a question which involves a dihedral group, and you need to know that the elements have order 2 and it's part of a larger story, then yeah, you can quote that result, right? That's the rules of the game in here. If you're uncertain about what you're allowed to just assume, ask me. Yeah.
Would you rather us prove by just direct algebra on like x to the n, or would you rather us do reduction?
I don't know. Prove by picture. Not entirely unreasonable. Yeah. But I think induction is not too bad here, if I remember right. But let's not get too far into the weeds on here on that. Where was I? I was handing something back here. Let me continue.
In addition to dihedral groups, do we need to really focus on anything else about isometries?
See, I'm not going to tell you not to study something in the first part of the course. So I want you to understand what we covered.
Is that interesting?
I will say this, when everybody gets a problem wrong, that doesn't make me not put it on the final. Let's see here. There is that. Where's Audrey? Ah! I saw her. I know she's around here somewhere. Jeremy? Ah, there you are.
So then is it fair to assume if it wasn't the one that it's open to know it?
No, I don't think that's accurate. I would say that what's on the test, of course, is generally reflective of the focus of the final. But, if I've covered it in here, I might put it there. I do like to see if you've actually studied the course.
Is the list of theorems that we need to know how to
For Lorenzo. I'm not helping.
Is the list of theorems that we need to know how to use, but not necessarily be able to prove any longer or shorter than it was for the previous tests?
Now that's fair. If I said that you don't need to know how to prove a theorem for a test, it's still the case. You don't need to know how to prove it for the final.
As any shrinking happen to the list of theorems.
So around maybe 3 theorems to a homomorphism.
Yeah.
You compile a list similar to what you did for test 3 about theorems that we should prove and theorems that we should not prove.
For the final, I don't really feel like doing that now.
We have to study all of it.
It's easy, it's everything he told us not to prove
Just
for
for
test
test
3.
one.
And it's all he told
Does
us
that
not to prove.
include,
Test
like,
1, that's it.
if you say it wasn't important at one time, like the power series representation of the polynomial stuff?
Yes.
That's not going to be the final.
Right. Right. I mean, if I have, it is generally fair that if I have ruled it out for a test, I probably rule it out for the final. But what I don't want to say is that if it wasn't on the test, it might not be on the final.
Only if you said it was like.
Yeah. Because I always have a list of like 40 questions and I can only ask you like 10 of them. And some of the other 30 I cut out are near and dear to me, so I just save them for the final. You know? Yeah.
So normally you write a test, and our testing time is about 15 minutes.
Yes.
I'm curious if you're planning on writing a more than 3-hour test, or or a 2-hour test that then we will have enough time for, or
Well, you know, have enough time.
Try and make that 10 hours after.
The question is,
If it could be short, that would
Are you creating a 2-hour test that might take us 3 hours? Or are you creating a 3-hour test?
this is my question.
I mean, my goal is to create a 1-hour test that might take you 3 hours. But
be. What about the length of our other tests?
Make your test near a black hole.
Yeah.
I don't know if these questions have meaning. I mean, we have 3 hours, so, you know, I mean, it's more fun.
My brother's in town.
Aaron in the back. Haha.
Also, does your brother have anything from test 3 anywhere? Because his stuff is only test 1 and 2 for us.
Yeah, no, Bill cheated his students out of like, you know, a couple chapters of material.
Clearly doesn't have the same love of abstract algebra.
Oh, sorry, there's no internet connection. We'll never find out.
I think we should take it.
But the link to his stuff is on your.
I don't think he has a test series.
I think that's unless it's in a different course, you know, but I didn't see it.
Yeah, I think you're clever.
Yeah, for real. I wonder if, yeah. I wonder if you Because he was specifically talking
I mean, I think you know, a lot of the proofs we've done have been pretty simple, right? And if you really boil down to it, boil it down, you think about a lot of the things we've proved in here. In another book, there might be an exercise, right? So those are the ones I'd worry about the most. You know, anything that you could see as a homework exercise in another book, those make nice exam questions. For example, on your last exam, you had proved that what is it? How'd it go? Trying to remember. Words. It's a good thing I don't have to say anything today. It's here. Where'd that thing go? Where is it?
I think one of them was PID.
Yeah, that's what I'm thinking of here. This thing, right? R be a commutative ring with unity. Let A be an ideal of R. Prove the quotient ring R mod A is an integral domain if and only if A is a prime ideal. I mean, yeah, there's a lot of writing here, but when you get down to the logic of it, really what do you need to know? Definition of a quotient ring, right? What does it mean to be prime? And so if you understand the basic definitions of this material, you don't have to be that clever to come up with this proof. I mean, I wrote it down without looking at a book, so it can't be that hard. You know? I mean, seriously. So, on this one, you know, if you understand what the words mean here, there is a legitimate chance you could prove this without having studied the proof before. If you understand the definitions and you just use logic and work it out and have confidence in yourself that you can prove things, you've got a shot at this problem. You don't have to memorize everything.
But can we get it done in the, like, 5 minutes that we have? Let's take a slot for that.
Like I said, a 1-hour test with 3 hours. So, yeah, exactly 15 minutes of 5. I was getting to something. Oh, we were hunting my brother's final, right? If the internet will let us. What exciting picture of Bill's children will we see today? All 4 of them. Hooray. All right, let's see here. I don't know. I think he's got, where is it? Old exams, I think. And then abstract algebra.
So you don't have abstract algebra too?
No. I mean, sort of. But. Oh, here it is. Look. Answer key. Not a Rickroll either. Let's see here. It's unfortunate you asked about this because now I can't use it.
It's true, because I would have been looking at it anyways.
You just read through and have those questions roll in the back of your mind.
Oh, so this is that material. Okay. Is this his modern algebra?
Mm-hmm. Yeah.
Okay. Modern algebra is abstract kind of.
Yeah, modern algebra is abstract algebra at other schools.
Right, because he has abstract algebra 1 and then he has modern algebra.
I don't know exactly the demarcation there, but I mean, I will say these are all pretty much fair questions for what it's worth. But
I bet you if you ask me the definition of a ring on this final, no one's gonna get it.
Lorenzo's trying to use the reverse psychology on me again. See, I could ask what the definition of a ring is, but I really don't want to grade that. Oh.
It's all right, you don't test us on
I test you on definitions all the time. Ah, I see what you did there. Very nice. Fish me in there for a second. Okay, so let me go back here.
By example.
You know, to get a bird's eye view here, the course planner is helpful, I think. Stop that. Microsoft Word. You're stupid. Come on. Oh, thanks. I mean, obviously you wouldn't want to make Control plus resize the document. That would be crazy.
No, because that piece goes, it like does like subscript.
But everything else on Earth uses Control plus to. But yeah, it's a subscript macro or micro or whatever. Yeah, so before test 1, we did what? We did the basics. We did, the dihedral groups, geometric symmetries. I think most of you could afford to read through that section again. There's lots of simple questions I can ask about symmetry groups that I don't think you could answer right now. Many of you. I mean, I can't judge because the first test was too long, so you didn't really get to the last problem. But could you do the last problem? I don't know. That actually involves some legitimate linear algebra, that last problem. Cyclic groups. We had all kinds of cool problems about counting subgroups in terms of like orders of elements and things. Those problems are interesting. They make nice questions. Permutation groups, there's all kinds of calculations about permutation groups, right? I mean, there's lots of interesting permutation calculations. That makes kind of like a nice sort of gimme question on the final, right? Just calculate this about permutations. If you've understood the cycle notation, then you can get that one, just kind of put your brain into neutral and calculate, right? I would think that's a gift. It's kind of like a chance to relax from the proofs or whatever.
One doesn't require
Too much computation. Yeah.
timelines.
So isomorphisms, of course, are important. Let's see here. Is there anything we didn't actually cover? I mean, CELO theorems aren't on the final, right? And I don't really have much to ask you about finite simple groups. We didn't dig that deep. You didn't really have homework, you know? Group homomorphisms are, of course, important. I might ask you to prove the first isomorphism theorem. That's certainly something I might ask, right? So there's a lot of substructure there in terms of, you know, just showing that the operation was well-defined, right? A lot of you shied away from that well-defined operation question on test 3. Major gap in your armor. You should understand how to prove things are well-defined. Maybe it's the details of that problem that made you shy away from it, but I hope you understand the general idea that to prove something's well-defined for when we have an operation defined on cosets, we have to show that it's independent of the representative, right? So you have to assume you've got x plus a equals to x prime plus a, y plus a equal to y prime plus a, and then show that x, you know, that the choice of x or x prime or y prime doesn't change the outcome, you know? Yep.
Like, as far as like sometimes in the homework way to do things, I think there was like 2 or 3 different problems where it was like, for example, show all of the possible like homomorphisms between like 2 spaces, things like that. Like, what's the correct way to go about that? Or, like,
So I had a chance to talk to Bill about that, and I was hoping that he was going to tell me that the way I was doing it was like dumb, but he kind of just told me that the way we were doing it is the way you do it.
What was that again?
Well, if we're looking for ring homomorphisms, to start with, you can basically knock down some possible mappings just by looking at the fact that it needs to be an additive homomorphism. Right? Every ring is first an abelian group under addition. So we have theorems about possible homomorphisms between abelian groups under addition, specifically Zn. We have that problem 72, which gave us the specific, basically it has to be, phi of x has to equal to mx, and there's a condition that relates m to the size of the domain and size of the range. Don't ask me to state it offhand, I'll get it backwards. But you could easily remember a specific example to keep you on the straight and narrow there, right? Like our, from Z4 to Z6 was it, and multiplication by 2 or something, I forget, but anyway, you should go back and study problem 72. Problem 72 is important. The one about the homomorphisms from Zm to Zn. So that narrows it down considerably, right? So then you have a list of possible additive, you have a list of possible mappings which satisfy the additive condition for the ring homomorphism. And then, of course, you have to take care of the multiplicative condition. And then that pretty much boils down to you need to have a solution to like a squared, how's it go? A squared equal to a or something like that. Subject to the...
It's like think of all possible things and then rule out the ones in certain areas. I feel like it's just like forgetting something, some weird defined function that could be possible.
Well, again, you have a list of, you know, the additive structure is very, very demanding. We have that all homomorphisms have the property that they're just multiplications by a given number with respect to the modulus. So that gives you a finite list of things to look at. And then you just you can narrow that down further by looking at the a squared equals to a condition like we saw in the other problem.
What about multiplication?
As far as I know, there's no like super slick secret way. I mean, it's just whenever I come up with a question like that for Bill and he doesn't like it, he always says something disparaging, like it seems like a number theory problem. But it's just kind of it's a detail problem, yeah.
So there were a couple of different instances in especially ring homomorphism section where it was like, here's this theorem, it's exactly like the group equivalent of this theorem. So look at that proof to prove this.
Right.
Are you more likely to ask for those proofs in groups or more likely to ask for those proofs in rings?
That's a good example of something that I might like to ask on the final that I ruled out for test 3 now that you bring it up. I will admit, as I was writing test 3, I was very much bothered that I had promised you guys I wouldn't ask about the proof of those things. Because some of those would make pretty nice, like relatively simple questions that I would be more wise to not rule out. Specifically, I'm talking about
I feel like if you want to just change your mind and tell us which ones are back on the table.
telling you now. Let's see here. As soon as I find it.
As quickly as possible.
Oh, Eisenstein's criteria. You should know that, yeah?
No or no?
Prove it? No, I don't. I will. I promise I will not put the proof of Eisenstein on the final. There you go.
That's one.
Are you happy? It's really not that bad. But anyway.
Yeah, would you find that interesting?
Where'd you go, you stupid thing? Oh, here it is. Like, these make nice questions, honestly. I know we haven't done all of them, but I mean, some of them make nice questions. Some of them are just as tedious as they ever were. Like, I think the proof of 1 is pretty tedious. Like, proofs of exponent laws usually involve a split. You have to do induction for different cases and stuff. But on the other hand, proof that phi A is a subring of S, well, that's a nice question, actually. That's like a honest-to-goodness decent test question. I really shouldn't rule those out. On the other hand, I don't really think you need to study them per se. Like, I don't think it's something you necessarily should try to work through before the final. Like, you should know what these words mean and be ready to try to do it. If you're trying to memorize solutions to everything, I mean, you should have stopped doing that after Calculus 1, really. Right? Anybody who can memorize their way through Calculus 2, whoa. I just say whoa. I can understand how you could memorize your way through Calculus 1, but that's about it. I mean, past that, I don't know. But people try to do it. I know this because I see mostly logical proofs that have something just crazy in the middle. And it makes me realize, oh, they don't understand anything they're doing. They're just copying something down from memory. Oh, no. So we don't like that. Because our goal is, you know, this is not a course in whateverology. We're not just trying to make you repeat what we told you. Right? We want you to learn how to prove things like we do in here. I said whateverology.
I was saying your psychology.
I was being generic in my dismissal of other fields of inquiry. So
We know you're correcting it, though.
I was.
Biology, or even worse, zoology.
Yeah, those zoologists are the worst. They can't even decide which animal to study. No, we're going to study them all. What's that about? Sorry, I've got no real insults for zoology, so I just, Yeah. Uh-oh. Wait a minute. Why am I even... after I say something like that, then I'm going to Mr. P. It's a mistake on my part. Go ahead. I'm going to regret this.
I'm pretty curious what Bill looks like.
Oh, what Bill looks like? That's a fascinating question. I don't know. I mean, you can go... I think if you watch his website long enough, you'll see him. Yeah, he doesn't look anything like me. He looks more like... He's taller than me, and he's got more gray hair than I do.
Does he have a Facebook account?
Is he on the Book of Face? I don't know. Maybe I don't know. But
Are you on Facebook?
Am I on Facebook? Not if I can help it.
But there is a fan page. Just FYI, I mean, you can post it there.
Yeah, let's
It's been going for like 3 years, so no, I don't know who started it.
I think I know.
What's it called?
It's literally just that, fans of Architect.
It's
I don't know who started it.
My wife looks at that on occasion.
She started it.
No. That'd be funny. You know, there's plenty of pretty simple, explicit questions to ask like this one, which are very revealing. Many of you couldn't do this one, you know. Let's see here. I'm trying to go back. Oh, this one, you know, I got a lot of you guys in problem 4 here, if I remember right. How many automorphisms of Z100 have order 2? Right? So the critical thing there was we proved that the automorphisms of Z100 is isomorphic to the group of units for Z100. And then we have wonderful theorems about how we can, you know, declassify, so to speak, or classify, maybe not really declassify. But anyway, rip apart groups of units into direct products of subgroups. Well, not subgroups, but smaller groups of units. So 4 and 25 being relatively prime allows us to do that. And then, of course, there's those very important results about how you can decompose powers of primes for groups of units, right? So those fundamental isomorphisms, I think we just attributed them to Gauss. We never proved them, but if you don't know those, that's pretty damaging, right? So there is some like bits of trivia you need to know in order to make headway in certain problems, right? So you'd want to know, for example, that u of p squared is isomorphic to z mod p squared minus p. That's a very useful tidbit for a question like this, right?
Is it u p cubed is equivalent to z b cubed minus p squared? Is it minus 1?
I forget right off the top of my head. I think it's minus p squared. I think it's.
One less power.
I think so. I mean, actually, the proof of that was essentially. I mean, that's the formula for the Euler phi function, and you can actually prove it by counting things. I modeled the counting one lecture, you may remember. It was over there. You guys talked me out of it, and then I shouldn't have been talked out of it. But one of those deals where I had the right thing, and then I got talked out of it, and then I talked myself back into it, and so you don't remember. But I think you were here. I don't remember. But anyway, the proof that like u of p squared is isomorphic to that is essentially tied to that. The fundamental formulas for simplifying the Euler phi function in terms of powers of primes, right? So those are kind of useful tidbits to know. Let's see here. You got to know how to prove a normal subgroup's a normal subgroup, right? How do you prove something's a subgroup? How do you prove something's an ideal? What does it mean for something to be a homomorphism of a group? What does it mean for something to be a homomorphism of a ring? What's that?
Can you go to test 1 real quick?
I can try. I think I'm still missing. I haven't posted the. There's a couple things I haven't. Oh, you want me to look at solution? So, you know, guys, if I want an induction and you give me a ... like, I might take off a point or something, but it's probably not going to be a big deal unless I say in the problem explicitly, please show by induction, right? If I say please show by an induction and you give me a ... argument, I'm not going to be happy, right? But there's still some partial credit to be had. If there's nothing mentioned explicitly in the instructions about induction and you give me a ... argument, I'm probably going to be okay with it, in all likelihood. I would much rather have a ... argument than no argument at all. You know what I mean? Where are we? Which
I
one?
think last problem that I wrote was on it.
Say again, which one?
It was, I remember there was a problem that had to do with finding all of the, we get to the bottom of this page, this one, where, except it goes to the dihedral.
Yeah.
And you didn't show any work there, and I was kind of confused. So basically it's, I see now after you showed earlier that we all have order 2 for y to xn minus y1.
Mm-hmm.
So it's basically when we do this sort of thing, we can look at the Z50 and we can pretty much gather all the elements of
Well, okay, yeah.
order 2 stuff.
Well, how many elements of order 2 are there going to be in the sort of rotational subgroup here?
50.
Well, in the just the...
Well, 51 without...
No, just in the rotational subgroup, there's at most one element of order 2.
Oh, rotations.
Because there's only one generator for a subgroup of order 2, because other phi function of 2 is 1. And basically, if n is even, you have an element of order 2, right? If n is odd, I don't think you do, right? Like if you look at rotations by 120 degrees, there's no element of order 2 in there. You got 120, you got 140, 240, you got the identity. There's nothing order 2 in there. So odd dihedral groups, which are, n odd. The dihedral group has even order, because the our dn has what? Order 2n, right? But only for n even do you get a element of order 2 in the rotation piece. But the reflection part of it, everything in there has order 2. And basically, the reason I haven't showed work here is because we had a homework that showed that, and I'm just bouncing off the homework, basically.
But that's how you got it.
A more complete solution would include proof that those have order 2. Yeah. So, the solution could be improved here, I think, yeah?
Just curious, because when I looked over that before, I was not aware of that. I just didn't think of that.
Hmm.
Good that you said that.
So, anyway, I guess we're out of time. So I will see you at the final. I should send an announcement out about when the office hours will be a Monday, but there will be some Monday. So, thanks guys.